on up and get what you need for trivia. We're going to be starting trivia in about, I don't know, probably 2 or 3 minutes. Quick question for you all. This is like a show of hands thing. How many of you, if I started putting trivia questions up here on the screen, how many of you would be able to read them? Okay, cool. Then you with your hands raised, you're going to do great at trivia. Everybody else is probably going to lose. We'll wait a few minutes and hope it gets a little bit darker, and I'll be sure to read the questions out loud as well so that everybody has a fair chance. We're going to go ahead and start trivia right now. I know it's still a little bit difficult to see, but I'm going to read the questions out loud to help you out here. And we're going to go back through them again. We're going to run through once. We're going to run through again. Hopefully you all have time to get your questions down. And if not, let me know, and I can go review some questions for you all at the end just to make sure that everybody's had a chance. So with that, wait, do I want to make some announcements first? Yeah, I want to make some announcements first. Okay, so yeah, welcome back to Astronomy on Tap here at Bad Jimmy's. This is going to be our, this is going to be our last one at Bad Jimmy's, at least for the time being. So, you know, big round of applause for Bad Jimmy's for hosting us. Astro on Tap started here at Bad Jimmy's, I don't know how many years ago, because I wasn't even around then. So this is where we started out, and we're super grateful to them for being willing to host us in our time of need after Peddler closed. Next month, we're going to be returning to what was Peddler's, which is now Bickerson's Brewing, brand new brewery out there in Ballard, on May 25th. So put that on your calendars. Put Bickerson's Brewing on your calendars as well, so you know where to go. And we hope to see you all there in just about a month. So yeah, we've got two great talks lined up for you today. And I'm going to introduce those speakers after trivia. So right now, let's get on with trivia. All right. So question one. This remnant of a supernova that exploded in the year 1054 is known today as the what nebula? And you have some choices here. And I'm realizing I might be in the way for people that are over on this side. So I'm going to... I'll come around behind the podium so that y'all can see that. Choice A is the Crab Nebula. Choice B is the Lobster Nebula. Choice C is the Prawn Nebula. And choice D is the Shrimp Nebula. This should be easy because that nebula looks like one of these, and it doesn't look like the others. So if you just look at the nebula, you can tell clearly which of those options it is. If you need to get a closer look at the slide, because it's still a little bit light out here, go ahead and come on up, take a look at it. Get real close if you need to, and then go back to your seat and fill your answer in. So again, this remnant of a supernova that exploded in the year 1054 CE is known as the what nebula? The A, Crab Nebula, B, Lobster Nebula, C, Prawn Nebula, or D, Shrimp Nebula? All right, question two. Normal stars can produce many of the elements in the periodic table, but only supernova are able to fuse elements heavier than what? A, silicon, B, calcium, C, iron, or D, mercury. Which of those elements can only be produced in a supernova? Or heavier than? Elements heavier than which of those elements can only be produced in a supernova? That is, again, A, silicon, B, calcium, C, iron, or D, mercury. And there's a periodic table up there if that helps you. All right, one more time. Normal stars can produce many of the elements in the periodic table, but only supernovae are able to fuse elements heavier than A, silicon, B, calcium, C, iron, or D, mercury? All right, question 3. True or false? Certain types of supernova can be used to measure how fast the universe is expanding. Is that true or false? Can you use certain kinds of supernova to measure the expansion of the universe? Question 4. For galaxies similar to the Milky Way, supernovae are expected to occur within them about every how many years on average? So in galaxies like our own, do supernovae occur on average every A, 5 years, B, 50 years, C, 5,000 years, or D, every 50,000 years on average? All right, one more time. For galaxies similar to the Milky Way, supernovae are expected to occur within them about every how many years on average? Is it A, every 50 years? No, sorry, A, every 5 years. B, every 50 years. C, every 5,000 years. Or D, every 50,000 years? All right, question 5. True or false? Evidence of past nearby supernovae can be found in Earth's geologic, ice core, and fossil records. Is it true or false that evidence of past nearby supernovae can be found in Earth's geologic record, ice core record, and fossil record? All right, question 6. And we're shifting gears a little bit here. We're going from supernovae to life, astrobiology. So, I hope that's not too abrupt a transition for anybody. All right. The Blank equation is a concept Sorry, I'm at a weird angle here. The Drake equation is a conceptual tool for estimating. All right. Maybe I'm trying to trick you. All right, that's the free space for everybody. All right, this is number 5 is the Drake equation. Write that down if you missed it. It looks like a 5 because it's cut off. Yeah, number 6, sorry. Number 7. An unusual radio signal received in 1977, whose origin is still debated today, became known as the blank signal after the comment its discoverer wrote on the computer printout. Is it known as the wow signal, the how signal, the pow signal, or the holy cow signal? I fucked up. All right, one more time. Question 7. An unusual radio signal received in 1977. Is it known as the A, the wow signal, B, the how with an exclamation point and not a question mark signal, C, the pow signal, or D, the holy cow signal? All right, question 8. The habitable zone is defined as the area around a star where temperatures are right for planets to support which of these? Organic molecules is A. B, liquid water. C, oxygen atmospheres. Or D, magnetic fields. All right, one more time for question 8. The habitable zone is defined as the area around a star where temperatures are right for planets to support which of these? A, organic molecules. B, liquid water. C, oxygen atmospheres. Or D, magnetic fields. All right, moving on to question 9. The Cassini spacecraft flew through geyser plumes, which are thought to indicate a liquid ocean beneath an icy surface on which solar system moon? Is it A, Titan, B, Europa, C, Ganymede, or D, Enceladus? One more time for question 9. The Cassini spacecraft flew through geyser plumes, which are thought to indicate a liquid ocean beneath an icy surface on which solar system moon? Is it A, Titan, B, Europa, C, Ganymede, or D, Enceladus? And the last question, question 10. Besides carbon, hydrogen, and oxygen, which elements are generally considered to be essential for life? Is it A, nitrogen, B, sulfur, C, phosphorus, or D, all of the above? And one more time for question 10. Besides carbon, hydrogen, and oxygen, which elements are generally considered to be essential for life? Is it A, nitrogen, B, sulfur, C, phosphorus, or D, all of the above? Nitrogen, sulfur, and phosphorus. All right, I'm going to run back through all of the questions a little bit quicker this time, just in case anybody missed any of them. So let's go all the way back to 1. This remnant of a supernova that exploded in 1054? Is that 1054? The exact year makes a big difference. Is known today as the what nebula? The Crab Nebula, the Lobster Nebula, the Prawn Nebula, or the Shrimp Nebula? Hopefully you can see that picture a little better now since it's a little bit darker. All right, number 2. Normal stars can produce many of the elements in the periodic table, but only supernovae are able to fuse elements heavier than A, silicon, B, calcium, C, iron, or D, mercury. Three, true or false? Certain types of supernovae can be used to measure how fast the universe is expanding. All right, you don't get long with that one because it's just a true or false question. 4, for galaxies similar to the Milky Way, supernovae are expected to occur within them about every how many years on average? Is it A, every 5 years, B, every 50 years, C, every 5,000 years, and D, every 50,000 years? Five, true or false? Evidence of past nearby supernovae can be found in Earth's geologic, ice core, and fossil records. Drake. 7. An unusual radio signal received in 1977, whose origin is still debated today, became known as the what signal after the comment its discoverer wrote on the computer printout. Is it the A, wow signal, B, the how signal, C, the pow signal, or D, the holy cow signal? I got like 4 people. Yeah.
Just for a second, I have 4 orders at Bad Mini. If anybody has an order that they're waiting on, just walk inside. I'd probably not.
Yeah, no problem. All right, 8. The habitable zone is defined as the area around a star where temperatures are right for planets to support which of these? A, organic molecules, B, liquid water, C, oxygen atmospheres, or D, magnetic fields. Nine, the Cassini spacecraft flew through geyser plumes, which are thought to indicate a liquid ocean beneath an icy surface, on which solar system moon? A, Titan, B, Europa, C, Ganymede, or D, Enceladus? And finally, question 10, besides carbon, hydrogen, and oxygen, which elements are generally considered to be essential for life? Is it A, nitrogen, B, sulfur, C, phosphorus, or D, all of the above? All right, if you're done with your trivia sheets, please quickly bring them up to the front and hand them to Meredith. If you're not done with your trivia sheets, finish them right now, and then bring them up to the front and hand them to Meredith. Bring your pencils too. Pencils too. We are poor graduate students and we cannot even afford golf pencils. So please return them. Yeah.
Are you a postdoc?
No, I'm a graduate student.
Okay, can you help me? I teach high school astronomy.
Oh, yeah?
And I was sent here with a question that I need to ask somebody.
Okay, go for it.
And I'm
Okay, we're gonna get those graded for you, and we're gonna announce winners at the intermission between our 2 speakers. But right now, we're gonna get on to our first speaker. I'm gonna have to run back in a second and what? Mics? Yeah, we're gonna have to do that. I'm gonna announce the first speaker, and then we're gonna take a very brief intermission for me to switch the PowerPoints and for us to switch live stream microphones. But our first speaker is Megan Gialluca. Megan. Yeah. I've got some notes here for a proper introduction. Brief ones. Megan Gialluca is a first-year graduate student studying atmospheres of exoplanets. She graduated from Northern Arizona University, where she worked on assessing the capabilities of JWST.
That's right.
And she is going to be talking about aliens. So, she's going to convince you in 30 minutes that aliens are real. How many of you already think aliens are real? Raise your hands. Okay, cool. So you don't need to be here. You can leave. Come back for a second, speaker. How many of you have seen aliens, and that's why you believe they're real? Okay, a few. Excellent. Well, okay, give it up for Megan. I'm gonna switch slides real quick.
Okay. Nobody's allowed to look at this. Good? Good to go? Can I start? All right. Well, it looks good here. Okay. Hey, everybody. How's it going? Yeah. I'm really excited to be here today. As Tyler said, I am a first-year PhD student at the University of Washington in the astronomy department. And I do, in fact, study the atmospheres of exoplanets. So today, I'm going to convince you in 30 seconds. Wait, that can't possibly be right. Unless a real alien here tonight. What? Okay. We're obviously just kidding. This is my roommate, Kim. Everybody give her a hand, right? It's not easy to get up here because you guys are really scary, especially these guys. I'm just kidding. Just kidding. No, but for real. I am going to convince you, hopefully, in 30 minutes that aliens are, in fact, real. So, to get started, let's do some vocabulary. What actually is an alien, though? So the first picture we looked at, like, yeah, that's what you think of, right? When I say alien, you think of the sci-fi little green men. I guess in this case, little purple men. And sure, that could be an alien if it's on another planet. Sure, why not? But have you considered bacteria? What if we discovered bacteria on Mars? Is that an alien? Yeah, that's an alien. What about, and this one's the tough one, so get ready for this. What about trees? If we discovered trees on another planet? Yeah, that's also an alien. So we need a definition. An alien is any life that's not on Earth. It's not just intelligent life or little green men or humans on Mars. So have I clickbaited you with this talk and coming here today? Yeah, probably, right? Well, surprise! This is a science talk, and I'm not going to talk about UFOs. Okay. So I put the asterisk next to life because what actually is life, though? And as it turns out, defining what an alien is incredibly easy. But what's really hard is actually defining what life is. And I'm not going to be able to do it here today in 45 minutes. I know I said 30, but it's going to be 45. I'm not going to be able to do it today, is what I'm saying. But let's get a working definition so that you can have something in your mind as life for the rest of the talk. So these are the three kingdoms of life that we define here on Earth. We have bacteria, archaea, and the kingdom of eukarya. And so just so we all know, bacteria and archaea are what we call prokaryotes. These are single cellular life that don't have a nuclei. So you, your dog, and all of your houseplants are all in the kingdom of eukarya. And so this is life. This is what we consider to be aliens if we find it on another planet. Okay, so the main takeaway here is that life can be many different things, and they are all technically aliens if we find them on another planet. Okay, so we've gotten through the definitions. So now I think it's time that I start making my case for why life must, or at least is surely very probably, to exist elsewhere besides Earth. So you're thinking to yourself, because obviously you're the opposition and you don't think aliens are real yet, surely the way life originated must be special. And I'm going to need you guys all to pay super close attention. I'm going to give you a really, really scientific explanation of how life originated on Earth. Basically, the daddy protein really loved the mommy lipid, and so they, I'm just kidding, had to stop that before it got PG-13, right? Okay, but no, seriously. I am going to tell you guys about how life actually originated, or at least our best theories. So the origin of life science, the godfather of this is usually attributed to be Charles Darwin, who in 1871 was pondering how life could have possibly originated, and he said, but if, and oh, what a big if, we could conceive in some warm little pond with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc. present, that a protein compound was chemically formed, ready to undergo still more complex changes. And the really funny thing about this is that although Darwin was just like pondering this weird thing that he saw, he was kind of right on the money, albeit in a very general way. But nowadays, we have much more concrete ideas for how life could have possibly originated. And the first one I'm going to start with, option one, is fresh water. So fresh water, this idea really centers around volcanic hot springs. And before I get too into this, I want to mention that this is not my area of expertise. I dropped the remote. So I'm going to be doing my best, but I did do my research beforehand, so don't worry about that. So the main idea here, and this was really fleshed out really nicely by Bruce Dahmer and David Deamer in their 2020 paper, The Hot Spring Hypothesis for an Origin of Life. And the idea here is that these hot springs would be filled with really nice organic material, the kinds of stuff that life really likes. And through evaporation cycles, lipids, which are fat basically, can actually trap proteins inside of them. In this way, they're sort of acting like a membrane to trap organic material inside. And guess what else has a membrane that traps organic material inside? The cells in your body. So this is how they propose that protocells formed over time would build up into microbial communities. So that's option one. Okay. Option two is life originated in the ocean. Most typically, people think this would be on what we call hydrothermal vents. So hydrothermal vents are basically underwater volcanoes, and there's two types of them. So the first type, which is shown here on your right, is called a black smoker. These black smokers are directly above magma chambers and are volcanic in origin. They're also slightly acidic, which doesn't sound important, but it's going to be important very soon. So remember that. So these black smokers can actually have microbes on them living and replicating themselves up to 250 degrees Fahrenheit. So this type of life is what we might call an extremophile, something that survives in extreme conditions, of course. The other type of hydrothermal vent, which is shown on your left, is what we call a lost city vent. And these lost city vents, as opposed to the black smokers, are highly alkaline, so they have very high pH levels. Not only that, but they're also off-axis, so the water that comes out of them is not directly in contact with magma chambers like the black smokers. And so what all of this is to say is that where these alkaline vents meet seawater, there's this strong pH gradient from alkaline to less alkaline. And that gradient is very, very, very similar to how your cells store potential energy. And so this proposal for life, one of the biggest things in favor of it, is that life started here because it was able to harness this natural pH gradient as opposed to coming up with it by itself naturally. And I got this information, just so you guys know, since this isn't my area of expertise, this all came from Hydrothermal Vents and the Origin of Life, which is a really nice Nature review paper on this subject. Okay, now the last thing that I have to talk about is panspermia. And this is actually more in my area of expertise because I did work in meteoritics for a little period of time. But the idea of panspermia is that life was delivered to Earth via an impacting event. And this sounds kind of ridiculous, and I get that. But this would mean a couple of things, right? If life was delivered here, number one, life already exists offside of Earth, right? My job's done. But number two, that also means that life is capable of planet-to-planet travel, which would also be super interesting. I don't even know where to begin to prove that life started this way, but it would be interesting. Most of the evidence for this theory comes in the form of meteorites. And I'm going to talk about one very famous example, which is called meteorite ALH 84001. This stands for Allen Hills, Antarctica, which is where the meteorite was discovered. This meteorite was found to have originated off of Mars and to be about 4 billion years old, give or take half a billion years, which would put it right at about when the solar system was forming. Now, what's really interesting about meteorite ALH 84001 is that it had a couple of really nice lines of evidence inside of it. Number one, we see these carbonate globules, which are these orange parts that you see in this picture. They're surrounded, this black layer is iron and sulfur, and then the white layer is magnesite. And I know that you're looking at me and you're like, wow, those are some nice words, right? And I'm like, yeah, I also don't really know what they mean. But what I do know is that within these carbonate globules, we also found something called polycyclic aromatic hydrocarbons, right? That's a cool word. I suggest you all learn it. It'll make people think you're smart. Case one. But anyways, what you really need to know about these PAHs is that they're byproducts of a lot of bacterial precipitation here on Earth. And so you're thinking to yourself, and I know what you're thinking, you're like, Megan, this meteorite was in Antarctica for how long? Obviously, Earth bacteria could have gotten in it. And I'm going to say to you, that's fantastic. Really good job, guys. That was really smart of you. But some studies in 1995 and 1996 were actually able to show that similar rocks and meteorites from Antarctica did not have the same distribution of PAHs in them. And so this to them was evidence that Earth bacteria could not have produced this distribution of PAHs. And that sounds, you're probably like, oh, that's pretty cool, okay. But the thing is, this is still highly contested evidence, which is the asterisk I want to put on this theory. Okay, so now that we've done this, we're going to don our science hats. I actually brought a science hat, but then I forgot to put it together before this. Okay. But we're going to don our science hats, and I'd really like to know which theory you guys think is the most plausible. So by show of hands, who thinks freshwater? Okay, some people, some real free thinkers in here. Okay, who thinks it's the ocean? Okay. Okay, and who thinks it's panspermia? All right. These guys are the most confident in their theory. I remember you guys said that, by the way, because when we figure it out, I'm going to give each of you a call and be like, you were wrong. Just kidding. Not going to do that. Okay. So anyways, moving on. So, yes, we have now talked about the origin of life. And hopefully we've learned together that it's not this magical phenomenon, it's actually just chemistry. And so by that logic, if these right conditions existed elsewhere off of Earth, then it's also plausible that life could have arose in those environments. So now we need to ask ourselves, are these conditions really special? And the short answer to that is probably not, no. But you guys expected me to say that, right? Could you imagine if I was like, yes? No, I was just kidding. So let's look at a couple of real potential environments where life could be. I couldn't possibly stand up here and tell you about every space rock in the universe with a little water on it, but I'm going to tell you about some of my favorite environments. So up first is my favorite moon, Europa. So I'm sorry to the actual moon, but this one's just better. So Europa is really interesting because it has been shown to have a subsurface global liquid saltwater ocean, which is really, really cool when you think about it, considering that we think that water was needed for the origin of life on Earth. How do we know this? Well, number one, we can see these fractures on Europa's surface, which are most likely caused by thawing and refreezing cycles of the water ice on the outside. Now, the actual structure of Europa, it has what we think is a 10 to 15 mile thick ice shell, and then underneath a 40 to 100 mile deep subsurface ocean. And how could this be possible, right? Because you're sitting there and you're saying to me, you're like, Megan, I thought that liquid water could only exist if you were in the habitable zone. I'm like, okay, that's a really good observation once again. You guys are killing it tonight. It's a really good observation. But what I would say to you is that Europa actually has another interesting process going on. I'm going to put the microphone down for this because I'm going to act it out. But what's happening is Europa is orbiting Jupiter. And Jupiter has a ton of other moons that are orbiting outside of Europa as well. And just because of gravity, What's happening is Europa is getting pulled by Jupiter, it's getting pulled by the other moons, and it's pulled by Jupiter, and so it's getting compressed and extended and compressed and extended and compressed and extended, and there's a lot of friction happening in the interior. What do you get when you have friction? Well, if you like rub your hands together like this, they get hot. And so that is how Europa is heating internally and actually staining liquid water underneath its surface. Very cool stuff. But Europa itself is not actually special. I mean, it's special in my heart, but it's not actually special. We see this on other moons too. So another fan favorite is Enceladus, and Enceladus is a moon of Saturn. And Enceladus is just like Europa, global subsurface liquid water ocean, we get it, old news, right? But the neat thing about Enceladus, and yes, this is a trivia question, is that Enceladus actually has plumes, geysers on the surface, which are showing us that it has geological activity on the inside, right? It could have these hydrothermal vents, which is one of our biggest ideas for how life originated. So that's really cool. What's even more cool is that we had this one mission. So this is the Cassini space probe. It went to the Saturn system. It ended up finishing its mission in 2017 when it took a death dive into the planet. But besides that absolute Shakespearean death, Cassini, before that, flew through the plumes of Enceladus that I'm covering up with my shadow, flew through the plumes of Enceladus and was able to measure water, carbon dioxide, carbon monoxide, and organic material in the plumes. What's more is that Cassini was able to look at the outer ring of Saturn that was being actively created by these plumes on Enceladus, and it found not only water, but also salt. And you're like, big whoop, I got salt on my table, I got salt in my body, like why should I care about salt? Here's why you should care. Because salt cannot be carried away by water that's going directly from a solid to gaseous phase. It has to be liquid to get that salt at some point. And so what that means is that's further evidence that the ocean in Enceladus is actually liquid water. Okay, so there can also be life as we don't know it, right? So we're talking about how does life get created, and it's us, and it's our animals, and it's our plants, but could life be created without water? Well, one example of this, well, I guess not that life has been created there necessarily, but one example of a really interesting environment that might have life as we don't know it is Titan. So Titan, and once again, these are Cassini images. Titan is the moon of Saturn, just like Enceladus. And what's interesting about Titan is not only is it the second largest moon in the solar system, it's bigger than Mercury, believe it or not, but it's also the only moon with a very substantial, dense atmosphere, which is really, really interesting. And not only that, but it is the second, one of the only two planetary bodies in the solar system besides Earth that has liquid on its surface. It has lakes, it has rivers, it has seas, and it has rain cycles. Not only that, but Titan might also have a subsurface ocean, just like Europa and Enceladus. And so you're probably thinking to yourself, like, wow, this sounds like a great vacation destination, right? There's nobody there, it's probably nice and quiet, unless there's life there, of course. But what I would say to you is not so fast, because the liquid rivers and seas and everything on Titan's surface are actually liquid methane and ethane, not water. But that is a liquid to facilitate chemical reactions. So maybe Titan has life as we don't know it. And now that you're all experts on Titan, we get to play my favorite game called Titan or Consequences. I mean Earth. Titan or Earth. Okay. So the rules of the game are super simple. I'm going to put two images. One of them is going to be a lake on Earth. The other, lake on Titan. It's your guys' job to figure out which is which. We're going to have an easy round and we're going to have a hard round. So to start with the easy round, and I'm going to get down so you guys can see it. Okay? All right. My turn to sit down. Okay. First round. Titan or Earth. Okay. I'm going to use your guys' direction. So who thinks that Titan is the lake on your left? Okay, lots of hands. Who thinks Titan is the lake on the right? No? See, look at that. That's Titan, that's Earth. See, great. Now this next round is going to be the hard round, so get ready for that. It's in black and white, so no cheating with the green. Okay, Titan or Earth. Good luck on this one. Okay, who thinks Titan is the left image? Okay, okay, some hands. I'm noting this. Who thinks tan is the right image? Okay, all right. Let's find out. I got some of you guys. Okay. Well, that was a fun game. Now back to the science. Okay. But, can we consider places outside of our solar system? Yes, we can. And I'm going to talk about one of those places, my favorite of those places, which is called the TRAPPIST-1 system, which is my research topic. Yeah. Did you guys really think I was going to give a whole astrobiology talk without telling you about my research? All I have to say is I had to do it to him. Okay. All right, let's talk about TRAPPIST-1. So TRAPPIST-1 is a star that is much, much smaller and cooler than our own sun. So we have this is our list of what we call main sequence stars. Our O stars are the hottest and the brightest and the biggest. Our M stars, which is TRAPPIST-1, are the smallest and the coolest and the dimmest. And the sun is pretty average, actually. Just like its inhabitants. I'm just kidding, you guys, kidding. Okay, so TRAPPIST-1 is one of the cool, small, dim stars. And because of that, all of the planets are packed in super tight to the star. And what's more is that TRAPPIST-1 has 3, not 1, not 2, but 3 terrestrial rocky planets in its habitable zone. So somewhere where they could potentially host liquid water on the surface. So you're like, wow, that's so cool, right? Right. Okay, so let's talk about my research, like what I actually do. Thank you. Okay, before I tell you what I do, though, because I need to get your unbiased opinions, who thinks that detecting Earth-like levels of oxygen on another planet would mean definitively that we discovered life? Show of hands. Tyler thinks so. No? Okay, who thinks that it would mean we probably discovered life? Okay, some hands. Okay. Cool. All right, so let me tell you about what I do. I study how planets lose their water and how planets lose their atmosphere. So I'm going to tell you a little bit about how this actually happens. And this is something we're trying to figure out for those 3 TRAPPIST-1 planets, is if they could retain any water. So let's imagine we have an atmosphere and it's just filled with water vapor. It's only filled with water vapor. What can happen is you have radiation, XUV radiation, which stands for X-ray and ultraviolet radiation, can come in from the sun, strike one of those water molecules, and split it apart into 2 hydrogen and 1 oxygen atom. Now, that can go on for a little while until you have an atmosphere where things high up in the atmosphere that are subjected to radiation get split apart, and then lower down, the water can sort of remain. And so now in this upper atmosphere, you just have a bunch of hydrogen floating around, you have a bunch of oxygen floating around. Well, hydrogen is a very, very light element. It doesn't have that much mass. And so when radiation strikes that hydrogen atom, it excites it and it causes it to move faster. And if that hydrogen atom achieves what we call the escape speed of the planet, it can actually escape that planet's gravitational pull and make its way into space. And so this is just going to keep happening. This radiation comes in, strikes the hydrogen, and the hydrogen leaves. And over time, because hydrogen is less massive than oxygen, you're going to have a lot of hydrogen leaving. And so in this case, the escape is limited only by how much energy is incoming to drive escape. In other words, it's energy limited escape. So energy limited escape happens, and eventually you get a bunch of oxygen that's left behind. So you have this whole layer of oxygen on top of your atmosphere. And all of a sudden, the radiation's coming in, and the radiation's like, I can't get to the hydrogen. What do I do? Well, the hydrogen wants to escape the planet. So the hydrogen is going to try to make its way through that layer of oxygen. It has to diffuse through it before it can escape the atmosphere. And so this is what we call diffusion limited escape, because the escape is limited only by how fast hydrogen can diffuse through the oxygen. So I'm going to give you a much better analogy in case that didn't make any sense. So let's imagine that we are all in Friday the 13th, okay? And Jason's coming after us, right? So what are we going to do? Are we going to stand here and talk to him? No. We're going to run away, right? Obviously, we're going to run. So we're running, and we're just like running through this field. And how fast you can escape Jason is limited only by how fast you can run, right? So your escape from Jason is limited by your energy. This is energy limited escape. So you keep running and running, and you're making your way to the end of the field. and you look behind you, and Jason's right there, like 10 feet away, just walking, because that's what he does, right? And you're like, oh my God, I gotta keep running. So you keep running, and eventually this field ends, and you hit a corn maze, because that always happens in those movies. And so you hit a corn maze, and you're like, oh my God, I can't just run through this, or I'm gonna like hit all of this corn. So you start pushing the corn out of your way as you run, right? So now all of a sudden, your escape from Jason is not limited by how fast you can run, but rather how fast you can push the corn out of your way. So you have to diffuse through the corn. Diffusion limited escape. Okay, so that's my analogy. Thank you. It's a good one, right? It's a good one. Okay. All right, so what's the takeaway here? You're like, Megan, what does this matter? Why do I care? Well, what we just learned is by this process, tons and tons and tons of oxygen can be left in a planet's atmosphere. This oxygen was not produced by life, but rather produced by radiated water. So the main takeaway is that new research, my research, makes us evaluate what we think of as a sign of life, in this case, oxygen, on other planets. So now let me ask you, and don't ignore this definitively, okay, now, who thinks that detecting Earth-like levels of oxygen would mean we probably detected life? Yeah, all those hands are down. Nice. Okay, great. And I guess like the caveat I should put on this is that I've only done this work for that specific type of star. So more work needs to be done in the future to assess other environments. Okay, so I went on a planned tangent. Let's have a recap. We first talked about definitions, what's an alien, what's life. We talked about how life could originate. We talked about different places in the solar system where that life could originate. And then finally, I told you guys about my research. So now you guys are all ready. You're astrobiology experts. And let me guess, you're going to go to a party because you guys look like party animals. And when you're at that party, you're going to be like super excited to tell everybody what you learned, obviously. And inevitably, when you do this, some dude is going to come up to you at the party, probably had too much to drink. Yes, I'm speaking from experience. And he's going to be like, well, that's all fine and good, but if life is so common, why haven't we found it yet, right? And you're like, wow, that's a really original thought. Nobody in history has ever had that thought before, right? But this is what we refer to as the Fermi paradox. And the bottom line is, why haven't we found life yet? We don't have good enough technology yet. It's really hard to detect these things. And when you detect these things, it's slightly different for intelligent life. When you detect these things, how do you know that it's really what you detected? For every biosignature, every sign of microbial life we have, there's a million non-life explanations for it. And so this is really getting to what we call standards of evidence. And so this is a very active and ongoing conversation in my field of how do we actually know we discovered life? And there's 5 main questions you got to ask yourself. Number 1, have you truly detected a signal? It wasn't instrument noise, it wasn't random noise. Have you correctly attributed this signal to the right source? All right, so that's just level 1, that's just detection. Then you get down here to interpretation and new predictions. So question number 3, I don't always forget the order of these questions. Question number 3, are there abiotic or non-life sources for your detection? Question number 4, is it likely that life would produce this signal in this environment? And finally, you have to ask yourself, are there independent lines of evidence that you have detected life? You have to have lots of evidence. You can't just say, I saw oxygen, there's life there. You can't just do that. You gotta have lots of things to say. And so this figure comes from a white paper that came out of a workshop on standards of evidence recently that was run by Victoria Meadows from UW, who's one of my research advisors, and Heather Graham from NASA's Goddard Space Flight Center. Okay, moving on. So James Webb Space Telescope, you know that this is going to come up. You guys know that this is going to come up. James Webb Space Telescope might be the first thing to make some of these really cool detections. And James Webb, after many delays, has finally launched last December. Yes, that deserves applause. Yes, billions and billions of dollars later, it has launched, and it's making its way to its correct orbit. James Webb might be the first thing to detect some of these species like methane and carbon dioxide in atmospheres of planets around small stars like TRAPPIST-1. How do I know this? Wow, look at that paper title. this was my last area of research, so that is why I'm qualified to make this statement. However, we won't really know until we start trying. Okay, where is James Webb right now? Because I feel like that this is important information for just everybody to know. Well, we are currently in the process, I say we, like I'm a part of it, I'm not. We are currently in the process of aligning the telescope. So we're actually on step number 7, the final step. But back in February, this whole process started, and it started with segment image identification. So in order to do this, JWST had to turn on one of its instruments, NIRCam. NIRCam starts collecting light and photons. And what they do is, and I hope you guys remember that this mirror is segmented. There's 18 separate mirrors making up this big mirror. And so at first they put, what the hell? Sorry. At first they put photons through the telescope, and they looked for which segment creates which image so that they know where the segments are actually on the detector. After that, they had to align the segments, which is a fancy way of saying they had to focus them, get them into focus. Then they had to stack the images. So what starts is you have this image with 18 different segments, 18 different images. And as we move from left to right, you stack images until eventually you only have one image of the star. So the telescope is just one telescope. And then that continues in step 4, where they basically do coarse adjustments to this to get the mirrors to think they're all one telescope. Step 5 is basically like coarse adjustments, except it's fine adjustments. And step 5 will happen throughout JWST's lifetime. Step 6 then is actual telescope alignment. So we've been using this one instrument this whole time, but now we have to make sure the other 3 instruments also work and are aligned. And then finally, step 7, iterate alignment for final correction. That is where we're at now. And whenever that is finished, they'll be ready to start commissioning the instruments, probably. Okay. Okay, so the last thing I want to tell you guys about is the Astro Deckital survey. So every 10 years, the field holds a Deckital survey to find out what are the goals of the field, where is the field headed, and what should we put billions and billions and billions of dollars into do. And so 2010 actually gave us JWST. 2020 has recently been completed, and it identified 3 pathways of interest: worlds and suns in context, which is where this talk and my research fits in, new messengers and new physics, and cosmic ecosystems. We're going to ignore those other 2 for now. Worlds and suns in context is exciting because it got awarded the flagship mission this time around. So it was a choice out of 2, LUVOIR, which stands for the Large Ultraviolet Optical Infrared Telescope, and HabEx, which is the Habitable Exoplanet Observatory. And what ended up happening was NASA called for basically a mashup of the 2. They called for a large infrared optical ultraviolet telescope with a 6-meter aperture. And if you think we didn't notice that they didn't just move the letters around, they're wrong. But I won't point that out here today. So this flagship has a goal of observing at least 25 Earth-like exoplanet atmospheres in orbit around sun-like stars. So it's going to be really, really exciting. And I think we have some very, very interesting detections in the coming decades. So with that, I know that I didn't stand up here and tell you guys about UFOs or my trip to go see this guy, but hopefully you ended up with something much, much better. Thank you guys so much for being here today. I had a really good time. Ah! Do you believe? Ah! They love me.
I love how Mike caught that.
I know. I hope it did. Hello.
Thank you. Great talk.
How long? Did I go over?
heard her take a breath. All right, we're gonna bring up the trivia answers in just a second. Do like the 4 fingers swipe. It's on a different window. Sorry about the rain, everybody. I forgot to put in an order with the weather service. That's my bad. All right. We're going to do answers to the trivia questions. This is a little bit out of focus, right? Yeah. Okay, that's probably not any better, but all right. Question 1. The remnant of a supernova that exploded in 1054 CE is known today as the what nebula? It's the Crab Nebula. Can't you tell? This is obviously a crab. Normal stars can produce many of the elements in the periodic table, but only supernovae are able to fuse elements heavier than iron. This may be, I have been informed that this fact may be contested by our next speaker, but it still counts for purposes of trivia. If you have a problem with that, let me know after the show. True or false, certain types of supernovae can be used to measure how fast the universe is expanding. That is true. Meredith, what type of supernovae are those? Type 1a supernovae can be used to measure the expansion of the universe. For galaxies similar to the Milky Way, supernovae are expected to occur within them about every 50 years on average. True or false, evidence of past nearby supernovae can be found in Earth's geologic ice core and fossil records. That is also true. Drake. If you got that wrong, you automatically lose. An unusual radio signal received in 1977, blah, 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 is known as the wow signal. We all wish it was the holy cow signal, but it's the wow signal. The habitable zone is defined as the area around a star where temperatures are right for planets to support liquid water. The Cassini spacecraft flew through geyser plumes, which are thought to indicate a liquid ocean beneath an icy surface, on which solar system moon? Enceladus. Besides carbon, hydrogen, and oxygen, which elements are generally considered to be essential for life? As you all know, if all of the above is an available answer, then it's always the correct answer. So the answer is all of the above. And that is all of our trivia answers. So now I'm going to announce some winners. We have a lot of winners. You all did great on trivia this time around. We have a 5-way tie for second place, and then 1 first place winner. So first and second place is the team Overfit. Where's Overfit? Give me a celebrate. Overfit. Did you leave? Okay. All right. Well, if you're not that happy to have won, then I guess you don't need a prize. All right, go Overfit. Okay, the second team, which I suspect might just be one person, to have gotten 9 correct is Joel. All right. The third in our 5-way tie for second place with 9 correct is the magnetic monopoles. Excellent. Yeah, no, I realize it's not plural, actually. It's magnetic monopole, so it's just you. Sorry, tripping on the cord. The fourth, are we at four now? Yeah, the fourth in our five-way tie for second place is the rocket socket robots. And the fifth in our five-way tie for second place is, you have a name that I can't say on network television, but fortunately we're just live streaming to the internet and I don't see that many children here. So, Super Clusterfuck with 9 correct. And our singular first place winner, having gotten all 10 correct, is, drumroll, please, Dan! Just Dan. Okay, you all get prizes for that. I have some prizes here. So if you're one of those winners, first place or second place, come on up and get a prize. I have these are some cool pins, like spacecraft pins with an eye. I really like these, so I'm gonna toss that back there. These are assorted little stickers and poster type things. There's a bunch of little Drake equation cheat sheets in here. If you want to remember the Drake equation. So come on up, collect your prize. Feel free to look through the bag. Yeah, thank you. Here. What? All right, everybody, we are back. We are ready for our second speaker of the night. All right, our second speaker tonight is Azalee Bostroem, who is a postdoc with the Dirac Institute at the University of Washington and is also associated with the eScience Institute. Azalee has worked on the Hubble Space Telescope, has taught programming, has studied exploding stars. She's done it all, and she's here tonight to talk about stellar autopsies, how supernovae can tell us about their massive star progenitors. So please, welcome Azalee to the stage. Here's this. I have to trade this with you real quickly. This is our live stream microphone. Yeah. And here's the answer for me.
Yeah. Okay.
Enjoy.
Cool. Sweet. Thanks, Tyler. Hi, everybody. So Tyler basically did my introductory slides. So let me start with the best part, which is the pictures. So this right here, this should have been a trivia question. This is Supernova 1987A. And this arrow is pointing to the star that exploded. And so this is probably one of the most famous supernovae. This was visible with the naked eye in the southern hemisphere. And I wanted to put this up just to give you a sense of how amazingly bright supernovae are. So star, this is a massive star. It's like maybe 15, 18 times as massive as the sun. So it's a big, bright star, but that's how bright a supernova is. So they're super strong, super powerful, these big explosions. And they're what happens at the end of life of stars that are between 8 and 30 times the mass of the sun. So I'm hoping by the end of this, you guys are as excited about supernovae as I am and what we can learn about massive stars from them. Tyler alluded to some controversy in the trivia. So I wanted to first get you excited about why I think supernovae are really, really important to study, not just to, stellar astrophysics, but to all of the universe. And so the first thing is that supernovae are responsible for most of the elements on this periodic table. So this is a periodic table, and it's color-coded by where these objects come from. So this is hydrogen and helium are coming from the Big Bang, and so they're colored in this blue color. And so all of these, I'm going to claim, are coming from supernovae. So exploding massive stars, that's a supernova. Exploding white dwarfs, those are also supernovae. And merging neutron stars may be a little controversial, but the neutron stars come from the exploding massive stars. You would not have a neutron star without a supernova. So I'm going to claim this for team supernova. And that means that when you look at this table, everything that's green, everything that is light blue, and everything that is orange is coming from a supernova explosion. And so without that, we wouldn't have life. We wouldn't have any of the last talk that we had. So supernovae are really important for giving us all of these elements. Additionally, if we kind of zoom out from this microscopic scale out to a galactic scale, this right here is a galaxy. And we're viewing it edge on. So this is the spiral part here, but you're viewing it from the side. And this right here is all of this outflowing gas and dust. It's being pushed out in both directions, and it's being pushed out by massive stars, their winds, and their supernova explosions. So these individual stars are all collectively contributing to how galaxies form. And not just that, but if we zoom out, so this box right here is about 16,000 light years. If we zoom out so that this little bar right here is now 32 million light years, so much farther, I'm going to show you let me start this video playing. So all of these little circles are clusters of galaxies, and you'll see little blue plumes start to explode out. There, one just happened here, happening here. All of these plumes are energy being ejected into the surrounding cluster of galaxies, and on a cosmic galactic scale, we're seeing the energy and the influence of these supernovae. So it's not just an individual star, it's not just individual elements, but it's on a cosmological, huge galaxy cluster scale that these are contributing energy. And then this piece is another piece of the trivia, which is that type 1a supernovae are used to measure distances. And we do this because we think that they're all the same brightness. And so if you have two things that are the same brightness, but one looks fainter to you, that means it's farther away. And so we can actually measure, we can calibrate how much farther away it is based on how bright it is. And so it's by measuring distances with type 1a supernovae that we discovered that dark energy exists, which we think makes up a huge amount of the energy in the universe. And that's where, that's how we use them to measure the acceleration. So dark energy is another way of talking about the fact that the universe is accelerating. Okay, so that's why I think supernovae are important. I'm going to talk not about those type 1a supernovae. Those are the exploding white dwarfs. I want to tell you about the ones that are coming from massive stars, and that's every other type of supernova. So I'm just going to call them supernovae. And I want to talk a little bit about how does a star become a supernova. So we're going to start with a cloud of gas and dust, and this is just kind of hanging out in space, and something happens that disturbs it. And it starts to collapse. And there are little differences in density throughout this cloud that get exaggerated as it collapses, and each of those little pockets of higher density become stars and star clusters. And so all of this collapses and gets denser and hotter and denser and hotter and denser and hotter until this key moment when the core of one of these balls of gas starts fusing hydrogen. And this is when it becomes officially a star, is when this hydrogen starts fusing into helium. And this fusion process emits energy, so it emits photons, and that halts the gravitational collapse. And so the star lives in this relatively stable state where gravity is pushing in and the pressure from this fusion process is pushing out. And that's where it lives most of its life. It lives millions of years in this phase. But eventually it burns through all of the hydrogen in the core, and it just has this core of helium, which it's not hot enough to fuse. And so now you don't have this fusion process, you don't have this energy pushing out, and so gravity takes over and it starts to collapse again. And so it collapses until this outer ring around the core that was fusing into helium starts fusing hydrogen. And then the core continues to collapse because that still doesn't have energy pushing out, and it collapses until it gets so hot and dense that it starts fusing helium into heavier elements like carbon and oxygen. And at this point, you have all of this energy going out, not just from the hydrogen, but also from the helium fusion. And this actually puffs up the star. And because it gets puffed up, the outer layers cool down. So it's this big red star. And we call it that phase the Red Supergiant Phase. Astronomers are very creative at their naming. So it's big and it's red. We call it a red supergiant. And so this process repeats itself over and over and over until, another trivia question, you form an iron core. So what you end up with is you have this big hydrogen envelope. No fusion is happening here, but then you have a shell of hydrogen where hydrogen fusion is happening. You have a shell of helium where helium fusion is happening. You have a shell of carbon where carbon fusion is happening, all the way into this iron shell. And iron is unique in that it's the last element that when you form it, you get energy out. When you fuse iron into heavier elements, it actually absorbs energy from its environment. So this process that the star has been maintaining itself against gravitational collapse by collapsing until it can fuse heavier elements that produce energy, that breaks down when it develops this iron core. And so that process, it just accumulates this iron core until that core gets so dense, so hot, all of these processes are happening that it collapses in on itself. And it collapses in so rapidly that all of those protons and electrons get shoved together and form neutrons. And it becomes a neutron star. So this iron core is what becomes that neutron star that's going to produce all of those orange elements on the periodic table. And neutron stars are incredibly dense. 1 teaspoon of a neutron star is 1 billion tons. So they're really, 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 really dense. And they have, so this core forms this neutron star. That's a great, life for it. But there's all of this material from the outside of the star that's falling in and hitting that neutron star. And it bounces off that neutron star and creates a shock wave going out. And so this shock wave reverses the direction of all of the incoming material and causes it to accelerate out. And that's the supernova explosion, all of that energy that's released from this material coming in and bouncing. And it's even that's actually not quite enough energy. And this was a big problem for supernovae. It was kind of the secret of the supernova community until about 10 years ago, that we couldn't get supernovae to explode in any of our simulations. And it turns out that when this neutron star is created, it creates neutrinos. It creates a huge amount of neutrinos. And these neutrinos are important for helping that shock accelerate outwards and help unbind the star. Okay, so we're going to so this is what happens. That shock wave then travels out through the star. It reaches the edge of the star. This is the point at which photons start coming to us. So this is when we observe a supernova, is when the shock is called shock breakout. So it's when the shock breaks out of the edge of the star. And this light can start to travel to us. And then this material keeps expanding. And so that's what makes, another trivia question, the Crab Nebula. So this is a supernova that this material has been expanding for a long time, but all of this material used to be a star. So this is a really nice picture of stellar evolution. This is what we teach in our introductory astronomy classes. It's a great story, but it's not the whole story. So it turns out that there's a lot of question marks about, does this really happen? And so the first question mark is, are all of these stars exploding as red supergiants? Because it turns out that 1987A, our closest, best studied example, didn't explode as a red supergiant. It exploded as a blue supergiant. So these are stars that are similar, but they're much smaller in radius. And so that makes them, they're hotter and bluer. And there's also some interesting work going on about maybe these are yellow supergiants that are exploding. So these are an intermediate radius. So we don't totally know which stars are exploding as which type of supernovae. We also have this picture that I showed you where we have kind of, this is called an onion skin model, where you have these different elements. But you'll notice that the big hydrogen envelope is missing. So we have some supernovae that explode where we can tell that there's no hydrogen in the star when it explodes. And so another question that we have is, are these stars, how did that star lose its hydrogen envelope? Is it that it was some kind of massive star that had these huge winds that blew all of that off? Or was it in a binary system and one of the stars just pulled all of that material off? And so we're still trying to figure out these supernovae that we observe that don't have any hydrogen, which stars are they coming from? And then perhaps the most dramatic question mark, I would say, is, are these stars supernovaing at all? Or are they, some of them, collapsing directly to black holes? And if they collapse directly to black holes, that means all of those elements they created never make it out into the universe. And all of that energy of the explosion also doesn't make it out into the universe. So understanding what fraction of these, if any, are collapsing is also really important for understanding things like that periodic table and understanding things like how galaxies are evolving and those outflows. So these are all big question marks that we have about how massive stars evolve that supernovae can help us answer. And so I think one natural question for me is, why would you use supernovae to study massive stars? Why not just study the massive stars themselves? And my first reason is that massive stars are really rare, which means that you want to be able to observe as large a volume of space as possible to be able to observe them in. And supernovae are really bright, which means you can see them at much greater distances. They also like to happen by themselves, whereas massive stars tend to form in clusters all on top of each other. So that means that you can see them at greater distances, and they're by themselves, so you can observe them and isolate exactly what's going on with that supernova much more easily. So I'm going to go ahead and cross these first two off. The last piece is, I mentioned that a lot of our uncertainty happens at the Red Supergiant Phase. So this is that final phase of evolution. And this is especially true of the final phases of the Red Supergiant phase, where the silicon's fusing into iron, or the oxygen's fusing into silicon. All of these happened on timescales of like thousands of years to tens of years. So the silicon fusion occurs on this timescale of 3 days. So looking at a star and saying, you know, it's about to enter this phase is really hard. I don't know if you guys have seen some of the talks on Betelgeuse, but we're at this point where we're like, it might explode sometime in the next 20,000 years. So that's kind of the certainty with which we can measure this kind of stuff. But the supernova explosion is this big like alarm telling us that this star just exploded. And if we can use that to then look backwards from that explosion and study the evolution, we can study these final years of evolution. And so the supernova gives us this beacon and identifier, like this is the time to pay attention to this star. Okay, and then finally, I want to talk about why we're in the golden age of supernovae. So all of these acronyms are surveys that are looking at the night sky every night, every few days, and they're discovering supernovae at more and more rapid rates per year. So it used to be that we had maybe 20 supernovae a year. We now have thousands of supernovae a year. So this here is a plot looking at the number of supernovae discovered each year. This is its axis. So we're now at maybe 3,000, well over 2,500. You can see how much this has increased just in the last 5 years. And when the Rubin Observatory comes online, Legacy Survey of Space and Time happens, this is going to blow this entire scale out of the water. So this is a zoom in of these little lines that you can barely see, because this is how many supernovae we're going to discover every year with the Rubin Observatory. So we're going to have 300,000 supernovae. This is just the hydrogen-rich massive star supernova. It's a huge, like orders of magnitude. So I'm really excited about this, but it also means that we're going to have so many examples of these supernovae that we can study, and we'll be able to make statements about these stars if we can figure out how to connect these supernova observations to the massive star observations. So that's what I'm thinking about now. Okay, so I want to take a step back and talk about how do we do this? What kind of observations can we make? And so the first thing that I use all the time, the first tool in my toolbox, is a light curve. And this is a description of how the brightness of a supernova changes over time. So I have brightness here, and I have time here, and I'm just looking at how many days after explosion, how is the brightness changing at that many days. So we do this with images. This is a really cool story. This is supernova, I think it's 2016 GKG. And an amateur astronomer had his camera out and was calibrating it. So he was just taking pictures of a random galaxy, and it turned out a supernova happened in that galaxy. So this red circle here is showing you where the supernova will be. It's not present at 1:44 a.m., but at 2:40 a.m., you can see there's a dot right there in the middle of that red circle. And that dot ends up getting brighter over the next 15 minutes, and so he can map how that brightness changes with time. And that's what we're doing here. So these are the earliest observations we have of a supernova, and it just was just by chance. Someone was just taking a picture of a random galaxy. So supernovae in general, they rise in brightness. Then they have a period of either flat or kind of shallow decline for about 80 to 120 days. They then rapidly decline, and then they kind of shallowly decline again. And so they fade over time. So we can't observe a supernova for an infinite amount of time. Eventually, they're just too faint for us. So the way that we get information out of these light curves is we model them. So we program a computer with all of the physics we understand about these stars, and we put in some input parameters, like what is the mass of the star we're exploding? How much mass has it lost over the course of its lifetime? It turns out stars lose a huge amount of mass over their lifetime. Sometimes half of the mass of the star gets lost before it explodes. What is the explosion energy of the supernova when it explodes? So we put all of these input parameters in, we let the physics run, and we look at what photons come out, and we build an artificial light curve from that model. And so we do this not just for one set of parameters, but for a bunch of sets of parameters. So here's an example where we're varying how that mass loss, the mass that was lost over the course of the lifetime of the star, is distributed around the star. So these numbers here represent different solar radii away from the center of the star that this is being observed. And the big thing I want you to see is that as we have material that's farther and farther away from the star, it changes what the shape of this light curve is. So what I can do is I can take my observed light curve and I can say which one of these does it look the most like. And that then allows me to say, okay, what were the input parameters for that model it looks the most like? And that tells me what that progenitor star looked like. So that's how I do it with light curve modeling. In a very broad, general sense, what we look at is we look at the rise, so how quickly this rises. That tells us about the radius of the progenitor and its explosion energy, as in the density of that outer hydrogen. Okay, so that's the light curve. The other really important thing that we study, or that we use to study, so if you've ever looked at a rainbow, you've seen a spectrum. Your eyes have measured a spectrum. And it turns out that if instead of looking at something like the sun or a white light source, you look at a source that's a single element. So right here is high intensity at very, and it turns out that where these lines occur is specific to hydrogen. Because these are coming, if you think back to like high school chemistry, these are coming fixed for each element, how far apart these energy levels. That's not helium or hydrogen. And we've identified elements like oxygen. This big line right here is this red line in hydrogen. We have some elements of calcium. And so we can use the spacing and what wavelengths these lines occur at to tell us what elements we're seeing in the cores of stars. Okay, so that's our toolbox. What can we actually learn post-explosion? So I've already mentioned we can learn about radius from the rise. We can learn about the mass loss history. So as this shock wave expands, it's going to pass through all of this material that was lost over the course of the star's lifetime. So that tells us about the mass loss. We can learn about the composition from things like taking spectra at different points in time, because at different points in time, those photons are coming from different places in that ejecta, which correspond to different depths inside the star. And then we can learn about what mass star was it that exploded in the first place. So I'm going to talk about the two things that I study because they're my favorite, mass loss history and the mass of the star that exploded. Anyway, so this is my favorite plot of how we really don't understand mass loss. So here I'm showing you brightness. So as stars get brighter, they have more mass loss. That's what this is showing us. But each of these are valid, still acceptable forms of what that relationship could look like. So it could be kind of flat, it could be really steep. And there's some mass loss that we're observing now that's like off this plot. So it's so much, it's not even here. So we have big questions about when do stars lose mass? How much mass is lost? What's the energy output of this mass loss? What speed is this material moving at? And questions like that. So mass loss is really uncertain. We used to kind of ignore it because we thought we could, but it turns out that we can't. Okay, so let me go back to our picture of what's going on. So we have this shock wave, It's expanding through the star. This is our shock breakout. This is when our photons start coming to us. But when I showed you this before, there wasn't this blue material around the star. So I want you to imagine that maybe 1,000 years ago, the star was losing some material. That material has spent 1,000 years drifting away. Then maybe 100 years ago, it started losing material at a different rate. That's maybe this second ring of material that keeps drifting away. Then maybe 10 years ago, it started losing mass at a different rate. That gives us this. So we have all of this structure of material around the star that was lost over the course of the lifetime of the star. So these photons travel through this material. They have very high energy. They don't just pass through it. They interact with it, and they excite it, and they ionize it. And so we actually see this in our spectra. So normally supernovae have these very broad lines like this, and this is because this material is moving in all directions, so it kind of smears out these narrow lines. But this material is not moving very fast. It hasn't been accelerated by the shock yet, because the shock is still at the surface of the star, but these photons are moving faster than that material. And so they ionize it, and we get these narrow lines on top of the broad lines. So we only see these for the first maybe 2 to 5 days after explosion. So before we had all of these amazing surveys, when we weren't discovering supernovae very early, we weren't ever observing this phase, and we didn't see this very often. But over the last maybe 15 to 20 years, we're seeing it more and more frequently. And so this is telling us that there is actually this material around most stars. Then after this material gets ionized, the shock expands and the ejecta expands, and it starts accelerating and interacting with this material. That produces its own photons, and that changes the way the light curve looks. So here, you can't see that well, but under these points here represent the light curve of a supernova. So these points are observed data. Underneath these points is a solid line, which represents our best model if we include material around the star. This dashed line here represents our best model if we don't include any material around the star. So you can see clearly here that having this material fits this light curve much better. And so when we look at this for a sample of supernovae, these are all a bunch of light curves at a bunch of different wavelengths for 4 different supernovae. That's all you need to care about. What we find is that more than 70% of this sample requires some kind of material around the star that we're not talking about when we normally talk about stellar evolution. When we look at how many stars do we see these narrow emission features in, we see them in at least 40% of the stars, but this is still very recent research. So this number you can't quite see is coming from 2019. So we're still very much figuring this out. There's active research in both of these. But my big takeaway from this is that mass loss is much more common than we used to think. And it's something that we're now evaluating when we look at massive stars and thinking about, okay, how are these stars losing mass? Okay, so that's our mass loss history. Let me get to progenitor mass. So this is what I'm currently working on. Okay, so our current approach to figuring out what mass star exploded is kind of a hybrid pre-explosion, post-explosion technique. So first a supernova explodes. This is our post-explosion. So this is supernova 2008 BK. And if you're lucky, after that supernova has exploded, you go back and you say, did I ever think this part of the sky was interesting for some other reason? And if you did, maybe you have, maybe you have a pre-explosion image. So this is an image that was taken of the sky from the ground before the supernova explodes. And if you very carefully align these images, you find that the supernova is perfectly aligned with this red dot here. And so you say, that's likely the progenitor. You publish your first paper. But then you wait for the supernova to fade and really prove that that star disappeared. So here you can see that that star has disappeared, and that gives us definitive proof, or as close as we're going to get, that that is the star that exploded. And so then we look at these pre-explosion observations, and we try and figure out what type of star was that. So this is called direct detection because you're directly detecting the progenitor star. And so this is a plot of all of the masses that we measure with this direct detection technique. And this is a confusing plot even to astronomers. But what we're looking at is if I take 15 times the mass of the sun, I go here, and then I say, okay, how many supernovae have exploded with that mass or less? So 15 supernovae have exploded with a mass of 15 solar masses or less. So this dashed line is the line that we expected these points to follow. And you can see they do a pretty good job down here, but then they start to deviate as we get to higher masses. And this solid line is the actual relation that they follow. And so we have this range of stars that we expect to see exploding, but that we don't see exploding. And this has been dubbed the red supergiant problem, or the missing red supergiant problem. And so the big question, which is a little cut off here, are our predictions wrong? So maybe these stars aren't exploding, or is our interpretation of our observations wrong? We can't go out and measure mass. We're using indirect methods to measure mass. And so to give you a sense of how these could be true, I say the red supergiant problem is a problem with too many solutions, not enough solutions. So this is a plot of the brightness here versus time. And each of these lines represents how a star evolves with time for a given mass. So this is a 12 solar mass star, this is a 14 solar mass star, this is a 16 solar mass star. So we go to those observations that we had before the star exploded. We figure out a way to measure the temperature, we figure out a way to measure the brightness, and then we plop it down here, say it lands here, and we say, oh, that must have been a 16 solar mass star. So that's the way we do this. But what if there was more dust than we were accounting for? That would mean that we would infer a fainter brightness, and maybe we would say that was a 14 solar mass star instead of 16 solar mass star. So it's possible that there's something going on in our observations that we're not accounting for. On the other hand, people have done detailed theoretical modeling about which stars are exploding. So this is that plot where we're looking at how many stars of a given mass or less have exploded. And this is our mass. And so if you look here, each of these vertical lines represents a model. The green ones exploded, the black lines imploded. So those are the ones that became those black holes we were talking about at the beginning. And you can see that right when we start missing these is about where most of these start to implode instead of explode. So it's possible we have a theoretical explanation and we don't know which of these is right. And there are other ideas as well. So for a single supernova, we can try and approach this with different techniques. So this is our direct detection technique. These are those lines I was showing you before for different progenitor masses. This is an observation we've plopped down. This star represents our best guess. These lines represent how uncertain we are in that best guess. And so we think it's somewhere between 13 and 15 solar masses based on those pre-explosion images. Post-explosion, we can measure the light curve. So the observations are here in blue, the models are here in red and black. And from these models, you can see they match the observations really nicely. We get a 15 solar mass progenitor. A third technique we can use, so this is our second post-explosion technique, is that we can look at the spectra we were looking at. So this is the spectrum of a supernova about a year after explosion. And we can look specifically at this oxygen line. And it turns out that more massive stars fuse more oxygen and make this line brighter. So here is a zoom in of that line, and this pink line is for a 12 solar mass star. There's a yellow line here for a 15 solar mass star. The green is a 19 solar mass star, and the blue is a 25 solar mass star. This black represents our observed spectrum. So you can see from this, we also measure a 15 solar mass star because that black line is right on top of this gold 15 solar mass star. So we have a consistent picture again for all of these. To me, this is saying maybe this is pointing in the theoretical direction, not the observed direction, because of things like we expect all of that dust to get destroyed by the supernova explosion. So neither of these are probably affected by that dust. But this is just one supernova. So what I'm currently working on, and I hope in the next weeks to months to have done, is I want to build this plot But instead of masses that are coming from direct detection, I want masses that are coming from this late time spectra modeling, from spectra taken a year to 2 years after explosion. So far, preliminarily, I don't see these high mass stars. So it looks like maybe they aren't actually there. And I'm using all of these awesome observatories, which I had to put up because night sky and observatories, to get the spectra. So we have everything from 2-meter telescopes with the Las Cumbres Observatory to 4-meter telescopes with the New Technology Telescope, 8-meter telescopes with the Gemini telescopes, and 10-meter telescopes with the Keck telescopes. So a range of different sizes for depending on how bright the supernova is. And so the final thing I want to talk about is looking at the future. I mentioned we're going to have all of these supernovae from the Rubin Observatory. So I'm thinking about how do we make use of those? We can't go with our current approach of modeling each supernova individually. We really need a huge grid of models that capture all of the different types of diversity that we see in these light curves. And so I want to take this picture of building models and I want to vary all of these. Right now we just vary progenitor mass, and that looks like this. So each of these different each of these different black to white lines is a model of a different mass. And this orange line is our favorite supernova 2013 EJ. And you can see it's not matching any of these. So we really need to vary more than progenitor mass. And that's going to be looking at things like explosion energy. So that'll increase how bright the supernova is. Or looking at things like where is that mass located? That'll vary how steep that curve is. So my dream is to build this grid of models that looks at turning all of these different knobs, varying all of these different things that we can use to model all of these 300,000 light curves that we're going to get every year from the Rubin Observatory. And then use this to say, okay, what were those 300,000 progenitor stars? What did the mass loss look like in those stars? What were the progenitor masses? And so hopefully with that, we can start to get a sense of what is the population of stars that are exploding as these hydrogen-rich supernovae. So I want to stop there and take any questions. Thank you, guys. Okay. Yeah. Okay.
The model that you build is based off of what we know, what our current understanding of astrophysics, right?
Yes.
Okay. So given that the number of observations that we're able to make is going to jump multiple folds with these coming surveys, is there work to build a new model based off of the observations, like saying using AI to build a machine learning model, to like use the data that we observe and then build a new model based off of maybe nuances that we can't see based on our current understanding? When you asked about, okay, how are we going to build a model based on just 300,000? Well, I mean, machine learning lets you pull in data, run it through, take the observations, and then build a model that can predict those observations predict the model based on the observations that you see.
Yeah, so that's a great question. So the question is with all of these observations coming in, have we thought about, instead of taking the physics we know and modeling them, taking the data and building a model from the data? And so I think that the challenge with that is you can build something that predicts the light curve very well, but connecting that then to what the physical parameters is hard, because that's not something that we're observing necessarily. It's something that we're inputting into the model and then seeing what comes out. But that's something that I want to think about in terms of thinking we can't model every possible progenitor or every possible parameter, but maybe we can build like a coarse grid and figure out how to interpolate between. And what if something falls between the two models we built? What does that look like? And I think there's definitely a lot of room there for machine learning and AI. And that machine learning is currently used a lot in classification and figuring out which type of supernova is this. And so I think you can also look at things like clustering and looking at like what fraction of supernovae have have really shallow slopes and what fraction have really steep slopes. But then you still need a way to connect that to physically what's going on.
Is the most dense that starts to absorb afterwards, starts to absorb as opposed to emit energy? Do we know why iron specifically is the element that, can we explain, like we can observe that absorbs energy after that? So can we explain why?
Yeah. So the question is, why is iron that last element that you get energy out when it fuses? And it has to do with the binding energy. And I think it has the maximum binding energy. And so in every other element, minimum. So in every before that, when you fused two elements together or two atoms together, the binding energy was less than the energy of the two atoms separately. But after that, the two atoms separately has a larger energy than the atoms combined. No, smaller energy than the atoms combined. And so that's why we have that effect. Hold on one second. There and then there. Yes. Yeah. Oh, yeah. So the question is, when I say the number of supernovae is increasing, is that because, like, in the universe, the number of supernovae are increasing, or is that because we're just getting better at finding them? It's because we're getting better at finding them. So one of the big advances is that the CCD, the detectors that we use, are able to image more of the sky at one time. And so instead of looking at like individual galaxies, we're able to look at a much broader area of the sky, and we're able to observe, we have more sensitivity, so we can observe fainter things with less time. So yes, it's our technology, not the number of supernovae in the universe. Yes?
Does the generation of star change your expected again?
What do you mean by generation of star? Oh, yes. So the question is, does the generation of star affect our observed spectra? And yes, so where the way we usually talk about that is the effects of metallicity, and that's kind of like how many elements were in your gas when you started making that star. So to some small degree it does. There are effects like the winds that blow off the stars are largely driven by the heavier elements. And so if you have more of those winds, or if you have more of those elements, you get stronger winds. So that does play a role, but in terms of what we observe in the spectra, usually not that big of a role. The other thing, though, that it makes a difference for is that some supernovae tend to occur in low metallicity environments. So we think that specific types of supernovae are coming from these stars that are maybe those first generation stars. And there are people who are studying kind of the theoretical, very, very first generation stars that are coming from population 3 stars, and what types of supernovae would those form? Yes, and then I'll come over there.
Like above a certain mass of star, you just like a up the outer layer where it goes
Yes, so the question is that upper mass limit influenced by mass loss? Very much so. So that is largely set. So a detail that I failed to mention is that I'm really talking about stars that have hydrogen when they explode. And so if you have more mass loss, you strip off that hydrogen, and maybe those are exploding as a different type of supernovae. So maybe those are these stripped envelope supernovae. Yes, question. Yes, they already are. So the question is, are these mega satellite constellations affecting our ability to do these observations? Yes. So the Reuven Observatory is already looking at like how can we possibly mitigate this effect, because they expect, I think, I don't want to put out a number, a large fraction of their observations to have these tracks through them. And we already see them in the surveys that are ongoing right now, that sometimes there's a satellite that goes right over your supernova in your image and you can't measure its brightness. So yes, that is definitely an effect, and it decreases our efficiency and our ability to find supernovae. Okay, guys, thank you so much. I don't know, Tyler, do you have closing words?
Oh. All right, thank you everybody for coming out. Yeah, finish your massive round of applause for Azalee. What a time. All right, and another massive round of applause for Megan. Good job, Megan. All right, thank you all for coming out. Again, our next event is going to be on May 25th, and we are going to be at Bickerson's Brewing in Ballard, which is where Peddler used to be. So if you came to our events before the pandemic or our first post-pandemic event, then you've been there before. So we're gonna be back there, back in their beer garden. Everything's gonna be just like it's always been. All right. So thank you so much. That's gonna be it for us tonight. So get home safe, and hope to see you all in just about a month.